So we looked at the contrast of the eastern and western boundary currents. Now let's look at the sea surface of the world ocean. Okay, we have looked at the climate zones of the ocean before, but this is much more specific. This is showing the sea surface temperatures. What do you see? You do see kind of zonal structures in sea surface temperatures, which correspond to the zonal winds that force the currents, and the currents attract heat around, and so on and so forth. And nonetheless, you see that we kept looking at the longitudinal mean or zonal mean meridional sections to learn about the Hadley cell, the ITCZ, and so on. But when you open it up, you can see here clearly that there is a strong zonal contrast in sea surface temperatures in the Pacific and Atlantic Oceans. Okay, so you can see if you focus on the equator, you have much colder temperatures in the eastern equatorial tropical ocean around Galapagos, for example, compared to the western parts around New Guinea, northern Australia, Indonesia, Philippines, and so on. Okay, so the winds are not only pushing the water westward, the waters are getting heated along the way, and they're getting piled up on the west, so water is getting warmer as it's traveling west. But in the east, we will see that the winds, as they are pushing the water are near the equator, the water is diverging from the equator because Coriolis is pushing the waters to the right of the direction of motion in the northern hemisphere, to the left of the direction of motion in the southern hemisphere, which means waters are moving away from the equator, like Moses parting the Red Sea. What should happen when that happens? Cold waters have to come up to replace the waters that are going away. And if you remember your temperature profiles, the thermocline and so on, if you bring up subsurface waters, they are colder. And they also are rich in nutrients, so there is light near the surface as well, so you bring up nutrients and cold water with upwelling, you add light, you end up producing a lot of phytoplankton because of photosynthesis, for example, right? Whereas in the west, the waters are warm and the thermocline is deep, no nutrients available readily, even though there may be light. So productivity will be very low. We will look at that. So this is what I mean by connecting your concepts to each other, from physics to chemistry to biology, and a little bit from biology to physics, but we won't do much of how biology affects the physics in this course. Okay, so you can see that there are warm temperatures in the west called the Western Pacific Warm Pool, which also extends into the Indian Ocean on this end, so it's also referred to as the Indo-Pacific Warm Pool. And the cold temperatures in the east are referred to as the cold tongue. So that's colder temperatures, and they warm along the way. And you have the temperate latitudes and subpolar and polar latitudes. Okay, so you can see the California current and the Peru current on the east here. Those are the eastern boundary currents. And you have the East Australia current and the Kuroshio in the Pacific, and Gulf Stream and the Brazil current in the Atlantic. You have the Canary current and the Benguela current on the eastern side of the Atlantic, and you have the Agulhas current in the Indian Ocean. Okay, we will look at the Indian Ocean circulation later on, and we are not showing it in the northern Indian Ocean, obviously, because of the monsoon it changes. Okay, so this is showing also the seasonal cycle. Okay, you can try to guess if there is no information here. Okay, it's hidden. That's good. So the map above, you look at the warm temperatures, let's say around New Guinea and Philippines, in the two charts, one on top and one on the bottom, and can you say which season is which, right? So obviously, if all the warm water has moved to the north, that's because the sun has moved to the north and the heating is to the north, and that's because that's the northern summer. So the top figure is probably for July, and the bottom figure is probably for December. Could be June, July, August, or November, December, January, but nonetheless this is more like July, this is December. So the entire warm pool moves with the sun. What does it remind you of? The animation we saw of the intertropical convergence zone, which was moving with the sun, right? So the maximum heating, maximum rising air, maximum convergence, maximum rain, etc. also move with the sun. And you can see that here in this orangish colors extending from the Western Pacific towards South Central America. Especially here in December, it's become much thinner. So ITCZ is moving north and south. Under the ITCZ, winds come together, there is convergence, there is warm air. Okay, and in the Indian Ocean, you can see most of the year it's warm compared to the tropical Pacific and Atlantic Oceans. Indian Ocean doesn't have a very strong divergence and upwelling on the equator, whereas there is strong upwelling and cooling along the Somali coast, where we have strong Somali jet, which we will see later on. But you also remember when we looked at the wind energy map, the Somali region had high wind energy potential, so winds are very strong. Okay, so these are things that you should just kind of have it etched in your brain, so that when people are talking, or when you are talking about sea surface temperatures, winds, ocean currents, oceans, different oceans, and so on, all these things should just come to your mind. The distribution of temperatures, currents, winds, and so on. Okay, very critical to remember these sorts of details. So we'll move to the next part in the